The recent observations of the interstellar object 3I/Atlas have raised a series of puzzling questions about its physical behavior, particularly regarding its rotation and the unexpectedly coherent jets observed in the latest images. During July and August of 2025, the object's rotation period was inferred to be about 16 hours, with a very small uncertainty of merely plus or minus 0.01 hours. Such precision allowed astronomers to be confident that the nucleus of 3I/Atlas was not tumbling chaotically, but rotating steadily around a fixed axis. Ordinarily, for a comet-like body expelling gas and dust from its surface, this rotation should manifest very clearly in the structure of any observed jets. Material ejected from localized vents tends to trace spirals or become smeared out due to the rotating frame of the nucleus. This characteristic pattern has been seen repeatedly in natural comets within our own solar system, which display graceful corkscrew-shaped plumes or diffuse fans whose geometry reveals the underlying spin. Yet, despite the well-measured rotation of 3I/Atlas, the jets observed last week appear remarkably straight, sharply collimated, and coherent over astonishingly large scales exceeding 1 million kilometers. This is perplexing because the thermal speed of typical sublimated volatiles, those gases released when ices are heated by sunlight, is around 400 meters per second. A particle traveling at that speed for the length of 1 million kilometers would require roughly a month to traverse that distance. If the nucleus of 3I/Atlas were rotating every 16 hours while emitting such material, the resulting plume should not hold a consistent direction. Instead, it should sweep across space, producing a jet that curves or blurs due to the rotating emission point. The image taken by F. Niebling and M. Buechner on November 9, 2025, however, shows narrow, ruler-straight jets extending outward as though fixed in orientation throughout the entire time the released gas was traveling. Such physical behavior appears inconsistent with the previously measured spin rate unless something dramatic altered the rotation, or the jets originate from a mechanism fundamentally different from simple solar heating and outgassing. One might initially consider whether the object's rotation slowed dramatically between the summer measurements and the November observations. In principle, strong asymmetric outflows of gas can exert torque on a cometary nucleus, either spinning it up or slowing it down depending on the geometry of the vents. However, in most documented cases within the solar system, outgassing tends to accelerate rotation, not reduce it. The uneven release of material typically imparts additional spin rather than damping it. Therefore, the likelihood that the rotation rate of 3I/Atlas decreased significantly enough to explain the static orientation of the jets seems low unless an extraordinary and finely tuned set of torques acted on it. Without any direct rotational measurement taken in the past few weeks, the possibility cannot be completely ruled out, but it remains improbable based on standard cometary physics. Fortunately, new data expected soon may help clarify whether the rotation rate has undergone any unexpected change. Another idea, more consistent with typical physical processes, is that the jets appear coherent not because the nucleus has ceased rotating, but because the sublimation is occurring under highly restricted geometric conditions tied closely to the illumination by the sun. If 3I/Atlas possesses a complex surface topography, deep valleys, steep cliffs, and pockets of ice shadowed for most of the rotation, then sublimation might only occur when the sun illuminates the icy pocket at a very specific angle. In this scenario, a narrow jet would erupt only when sunlight reaches into the crevice, meaning that each period of illumination, repeating every 16 hours, would produce a discrete puff of gas. Over time, these puffs would be spaced along the jet at intervals equal to the thermal travel distance in one rotation period, at a speed of about 400 meters per second and a rotational period of 16 hours. This spacing would be approximately 23,270 kilometers. A single million-kilometer jet would therefore consist of around 43 distinct pulses or Ps, aligned along the jet's length like beads on a string. Such a structure is entirely consistent with the physics of intermittent jetting due to periodic solar illumination and a complex terrain that restricts the sublimation to only certain moments. However, this explanation introduces another problem: the direction of the observed jets. If sublimation is controlled primarily by sunlight reaching into specific surface features, the jets should generally point sunward because the heating is strongest when the surface faces the sun. Any puff that emerges when the pocket cools or when the sun moves out of alignment would rapidly diminish. Thus, the overall jet orientation should trace the direction from the nucleus toward the sun. The observations taken on November 8, 2025, by M. Yeager, G. Riemann, and E. Prosperi showed jets extending in directions not aligned with the sun, and in some cases even pointing away from it. This detaches the sublimation-driven explanation from the observed geometry. A sunward jet is conceivable, but anti-sunward jets from illumination-driven vents require reflection, re-radiation, or other secondary processes that are generally much weaker than direct heating. The presence of jets with orientations inconsistent with the sun's direction reduces the plausibility of a purely solar illumination-driven model. Another scenario is that these apparent jets are not jets at all in the traditional sense, but rather the extended trails of fragments that have broken off from the main nucleus. If the nucleus underwent a fragmentation event or explosion near perihelion, individual pieces could have been ejected at high speeds, each leaving behind a trail of gas and dust that appears as a long, narrow feature. In such a case, the orientation of the jet-like structures would reflect the motion of the fragments rather than the rotation of the original body. This would allow for directional stability over long timescales because a fragment moving in a straight trajectory would shed material along that path. However, this interpretation conflicts with images taken on November 11, 2025, by D. Jewett and J. Liu, which show the object as a single nucleus rather than a cloud of large fragments. If fragmentation had occurred, one might expect multiple distinct bodies, or at least a discernible elongation. The lack of such evidence makes the fragmentation hypothesis difficult to sustain unless the fragments are unusually small, unusually faint, or ejected in a manner that leaves the main nucleus visually intact. A far more speculative possibility, though not one that can be dismissed outright without further data, is that the jets are not natural at all. If the jets are produced by non-natural mechanisms, such as technological thrusters, then their coherence, directionality, and persistence would be much easier to explain. Thrusters would maintain a stable orientation regardless of the rotation of the underlying structure if the system were actively correcting its posture or applying controlled torque. Such a mechanism would allow the jets to maintain direction over millions of kilometers without the smearing effects expected from natural sublimation. While extraordinary claims require extraordinary evidence, it remains true that the behavior of 3I/Atlas has shown multiple anomalies that do not conform neatly to familiar natural processes. If the jets are artificial, they may serve navigational, stabilization, or propulsion functions, fitting within a technological framework rather than a geological or chemical one. Although such speculation is provocative, it arises naturally from systematically eliminating conventional explanations. Regardless of which explanation proves correct, the post-perihelion images add another layer of mystery to an already enigmatic object. There are now at least a dozen unresolved puzzles associated with 3I/Atlas, each of which deepens the intrigue surrounding this interstellar visitor. One of the most striking anomalies concerns its retrograde trajectory, which is aligned within just 5 degrees of the ecliptic plane, the same plane in which most planets orbit the Sun. Such an alignment has an exceedingly low probability, estimated around 0.2%, for an object arriving randomly from interstellar space. Yet 3I/Atlas not only follows this unusual path, but does so with a retrograde motion, raising questions about whether its origin or trajectory was shaped by forces beyond simple gravitational drift. Additionally, during its earlier observation periods in July, August, and early November 2025, the object displayed a persistent sunward jet, an anti-tail, that defied conventional expectations. Unlike typical comets, whose apparent anti-tails arise from geometric effects in the observer's line of sight, the sunward jet from 3I/Atlas appeared to be a genuine physical feature rather than a visual illusion. This further differentiates 3I/Atlas from natural comets, whose dust-tail geometries are well understood. The repeated appearance of a sunward plume adds to the list of phenomena that do not fit comfortably within standard models of outgassing behavior. The accumulation of these anomalies, ranging from its unlikely trajectory to its unusual jet orientations to the surprising coherence of its long-scale plumes, suggests that 3I/Atlas is not behaving like any previously studied natural object. Whether the explanation lies in unknown natural processes, extreme surface geometries, unexpected fragmentation dynamics, or something more exotic, the object continues to challenge established assumptions. As new observations arrive in the coming weeks, astronomers may gain the clarity needed to resolve its mysteries. Until then, 3I/Atlas remains one of the most perplexing interstellar bodies ever observed, pushing the boundaries of our understanding and reminding us how much of the universe remains unexplored.